Okay, so let us start. We will continue the study of Banach algebras and C-star algebras. We will also go into non-unital ones and we will see how to add a unit to that is identity to a non-unital Banach algebra, and so many of the concepts which we defined earlier will make sense even in a non-unital Banach algebra, and we will see that non-unital C-star algebras, commutative C-star algebras can be identified with continuous functions vanishing on a locally compact Hausdorff space. Okay. So, that is the difference we will see. Okay. So, let us start. So, just to continue the study of Banach algebras and C-star algebras. So, we have this proposition. So, let A be a unital C-star algebra. C-star algebra. Okay. If x is in A and x star equal to x star x. Okay. So, such elements are called normal elements, right. So, compare it with what you know for operators. If I have an operator t, then t is normal if t commutes with t star, right, that is t star equal to t star t, and that is precisely what we are saying here. And for normal matrices and so on, you have seen spectral theorem and certain consequences of that, and some of that continues to be true here. Okay. So, if x star equal to x star x commutes with x star, then the spectral radius is actually equal to norm of x, right. So, this is, you can compare it with what you know for normal matrices, you know it can be diagonalized, and the norm of that matrix, the operator norm, right, as an operator on Cn to Cn is actually the supremum or maximum of the modulus of the eigenvalues, and that is precisely the spectral radius, right. So, for normal elements, the spectral radius and the norm are same, and that is why the norm is unique, right. So, B, so one more curious thing, if again this happens because these are C-star algebras and so on. If B is a C-star algebra and phi from B to A. So, A is a unital C-star algebra that we already know, B is another one, and I have a star homomorphism. Of course, this is continuous. Okay. So, it is a bounded map. So, it is a bounded linear map to start with, and it is a homomorphism, that means the product goes to product. The star homomorphism means it also respects the star. Okay. So, phi of x star would be the star of phi of x, right, the adjoint of phi of x. Then it is contractive, then the norm of phi is less than or equal to 1 automatically. So, it is bounded, then if star homomorphism is a bounded star homomorphism between C-star algebras, then it has to be it has to have norm less than or equal to. Okay. Okay. So, let us prove this, and then we will go to non-unital Banach algebras. Okay. So, let C be the C-star algebra generated by x star and E. So, we are looking at the first statement, if x is normal, that is x equal to x star equal to x star x, that means x commutes with x star, right. So, these elements commute, right. So, if I look at the C-star algebra generated by these 3 elements, it is going to be a commutative C-star algebra with identity, right. So, then C is a commutative C-star algebra containing identity. See, here we did not assume that A is commutative. If A is commutative, of course, x star will be equal to x star x. We do not need to go down to a commutative C-star algebra. Okay. So, C is commutative. Now, by Gelfand-Naimark, rho x equal to that is the spectral radius of the element x. So, this is equal to infinity norm equal to norm x, right. So, that is what we wanted to prove, right. So, spectrums are same, right. So, we have seen that. So, we do not need to bother about anything about the spectral radius, and that has to be equal to the supremum norm of the Gelfand transform, right, then that is norm x. So, that is done. So, this is, as I said, for normal matrices you already know, and it is true in general. B is also in a similar fashion. So, let norm phi is less than or equal to c, strictly less than infinity. So, we have some norm, right, we want to show that it is actually less than or equal to 1. Okay. So, for any y in script b, we look at, okay, so phi of y star y to the n. Okay. So, this is less than or equal to C norm y star y to the n, right, because phi is a star homomorphism and so on. So, you can start with y star y to the n, and well, maybe I should have put the bracket here including y star y to the n phi, but that would be the product of those things, right, because phi is a homomorphism. So, you will get phi of y star y to the n, and that is less than or equal to y star y to the n because of continuity, and this is less than to c times. Use the Banach algebra property. So, that is you will get y star to the n, y to the norm of y star to the n and norm of y to the n, but norm of y star is norm y. So, whatever way you want to do, you will get to it, right. Okay. Hence, phi y norm square equal to norm of phi y star y, right, because phi of y star y is phi y star into phi y, but phi is a star homomorphism. So, phi y star is the adjoint of phi y. So, I have phi y star into phi y, and C star identity tells me that this is norm phi y square, right. This is equal to limit n going to infinity norm of phi y star y to the n to the 1 by n, right. So, spectral radius formula and so on, this is less than or equal to limit c to the 1 by n norm y square, okay, equal to norm y square, okay, from whatever we have done earlier. So, this tells me that the norm is less than or equal to 1. Okay. All right. So, that was just a amusing corollary that any star homomorphism has to have norm less than or equal to 1. Okay. Okay. So, now we look at, so let us move on to the next topic. So, this is non-unital Banach algebras. Let A be a, so non-unital meaning there is no identity, right. So, let A be a non-unital Banach algebra. We will see how it is for C star algebras as well. Okay. So, right now we will stick to Banach algebras. We will attach identity to it. Okay. So, for you can keep L1 of R as an example, right. So, this has no identity. We construct A tilde. So, A tilde is going to be a unital Banach algebra. We construct A tilde. So, a unital Banach algebra, okay, such that A can be identified with a maximal ideal. So, A can be identified with a maximal ideal inside A tilde, right. So, that A sit, so A will sit inside A tilde, right, in some form, where A is a maximal ideal of A tilde. So, let us do this. So, this is quite simple, attaching the identity. Okay, it does not serve the purpose for C star algebras, we will see how to manipulate it, but let us attach an identity to A, right. So, let A tilde be equal to A cross C, right. So, this is all elements A lambda, where A belonging to A and lambda belonging to C, right. So, you can give vector space structure, the natural vector space structure, and I want to define a multiplication and give a norm and make this into a Banach algebra, right. So, define a multiplication, right, on A tilde, multiplication on A tilde by, okay. So, I take A comma alpha and B comma beta, right. So, A belongs to script A, B belongs to script A, alpha beta belongs to complex numbers, and I want to define their multiplication. So, multiplication is simple, alpha and beta should come with the identity. So, it is like A plus alpha E and B plus beta E, you multiply them. Okay. So, this is equal to A B plus beta A plus alpha B. So, imagine if you are multiplying A plus alpha E and B plus beta E, you will have A B, beta A, alpha B, and then you have alpha beta, right, that is the scalar part. So, that is, you put that as the scalar part. Okay. So, remember this would be in A, script A, right, because A and B are in script A, alpha beta are numbers. So, and A B is in A and you are summing up things in A, right. So, that is how the multiplication is defined, and you can see that if A is commutative, script A is commutative and things like that, right. Now, in this multiplication clearly, well, what is the identity? Identity is clearly identity is 0 1, right. So, you have now you have a unital C star algebra, sorry, Banach algebra A tilde, right, and A is sitting inside. So, how is A identified? So, A is identified with, so you can identify A with A comma 0, right, A in A, okay, but we have not put a norm yet. Okay. So, what is the norm? So, define the norm, define a norm on A tilde. So, that is a new norm, but I will not write new and things like that. So, just write A alpha, okay, because there will not be any ambiguity, because this norm will reduce to the norm on A when you are looking at A. Okay. So, we are simply adding the sum, adding the norm of A and norm of alpha. Alpha is a complex number, so its norm is mod alpha, right. So, that is all we are doing, and clearly if this norm restricted to this restricted to script A. So, script A is identified with whatever is here, right, that is the norm in A, right, gives the norm in A, gives the original norm in A, right. So, A is sitting inside isometrically inside A tilde. Okay. So, we will identify A as a subset of A tilde. Okay. So, check that this is a Banach algebra norm, check that this gives a Banach algebra norm. Okay. So, that is that's easy, but it is also important because you need to know it is a Banach space, but that is trivial, you are simply adding up the norms. So, you would have seen that if I take product of two Banach spaces and add the norms, then I will get a Banach space. Banach algebra means you have to multiply and see that the norm x y is less than norm x into norm y is true, right. So, and we identify A inside this. The set A, so A is identified with A comma 0, with A in A, inside A tilde is a two-sided ideal and maximal, right, because the codimension is 1. So, these are maximal ideals. Okay. So, A is sitting inside A tilde as a maximal ideal. Okay. So, that is how you attach an identity to A. Okay. But then of course, how do you so you can define spectrum and things like that using the after adding the identity to a non-unital Banach algebra. Okay. So, if A is a star algebra, one can also define the involution. So, if A is a star algebra, that means there is a star operation on A, one can extend that to A tilde. So, we can make, that is easy, we can make A tilde also a star algebra by defining, I take A and alpha, I take the define the star to be, I know the star of A, that is A star, and simply put alpha bar, right. So, complex conjugation on the complex plane gives me a star operation. Okay. So, adding the identity is sort of easy when you have a non-unital Banach algebra, but let us try to understand it a little bit through examples. Okay. So, examples. Okay. So, take A to be L1 of R. Okay. In this case, it is a bit easier. Well, in many cases what happens is the non-unital Banach algebra already sits inside a bigger algebra which has identity. So, you just have to put the identity and generate the algebra, you will get what you want, right. So, in the case of L1 of R, we can look at M of R. So, what is M of R? These are all complex Borel measures on R. So, this is the space of complex Borel measures on R. Okay. So, that is a Banach algebra is a, so MR, so first of all it has a norm, right. So, if I take mu, a measure in MR, so that is a complex measure. So, there is something called the total variation. So, that is the norm, right. So, norm of mu equal to mod mu, right. For a complex measure mu, we have mod mu of R. So, that is mod mu is a finite measure on R, and this is the total measure, right. So, this is called the total variation norm, right. Mod mu is called the total variation measure, and this is the, and MR is a Banach algebra, MR is a unital Banach algebra, with respect to convolution. Okay. So, what is the convolution of two measures? So, let me define that quickly. I take mu and nu in M of R, then one can define mu convolved with nu. So, this is a measure. So, it is a linear functional on Cc of R or C naught of R, right. So, I just need to tell you what it is after integrating against a function, right. So, mu is defined by integral f of x d mu star nu of x integral over R, right. So, this you can do the following. So, this is f of x plus y d mu x d mu y. Okay. So, you check that the right hand side is actually a continuous linear functional, and that gives me a measure by Riesz representation theorem, and that is your convolution. Okay. You can also write it in the usual convolution form of mu and nu of a set A to be certain integral and so on. Okay. But this is an easier way of defining. Okay. Then M of R is a unital Banach algebra. Well, you have to check that. So, norm of mu star nu is less than equal to norm of mu times norm of u, which makes it into a unital Banach algebra. So, what is the identity? Identity is the Dirac measure at 0, right. So, let me identity for M of r is the Dirac measure at 0, right. What does that mean? So, well, let us call it delta naught. So, delta naught at A is equal to 1 if 0 in A, 0 otherwise, right. So, for any Borel set A, this is how the measure is defined, and you can check that mu convolved with delta naught, equal to delta naught convolved with mu equal to mu. Okay. So, it is a unital Banach algebra, and identity is the measure supported at 0, right. Like for Z, remember L1 of Z is actually the measures on Z, complex Borel measures on Z, and the identity is the one which has mass at 0, right. That is precisely what we are doing, except that on the real line we have to be a bit more careful. Okay. And well, how do you embed L1 of R? So, L1 of R is sitting inside M of R, right. How do you see a function as a measure? You just integrate with respect to that function, right. So, f going to f of x dx, right. So, in other words, this measure is given by integration against f of x. So, you are looking at the measure f of x dx, right. So, mu sub f, let us say at A. So, for f going to mu sub f, so maybe that is better way of writing. So, mu sub f, then mu sub f as a measure is defined to be integral over a f of x dx, right. In this case, the norm of mu sub f is actually the L1 norm of f. Okay. And so, L1 is sitting inside M of R, measures of R, and you have convolution of these measures which we define reduces to convolution of L1 functions. Okay. And so, when you attach identity, you just have to add delta naught, right. So, L1 R tilde. Okay. So, this is attaching the identity, right. For A we denoted A tilde. So, attaching identity is simply you look at all those functions f in L1 and then plus delta naught, right. Alpha is a complex number, right. So, this would be with respect to, so this is sitting inside M of R, right. So, there is a norm convolution, it is a Banach algebra with identity, and L1 of R is a maximal ideal there, right. Its codimension is 1. Okay. So, that is how you identify L1 of R inside M of R, and this is one example where we have attached identity. So, let us look at one more example. So, example 2, because these two, this is going to be important. So, now you take x to be locally compact but non-compact Hausdorff space. Okay. So, we have a locally compact T2 space, and we look at so our algebra is going to be C0 of x. What is C0 of x? All functions vanishing at infinity, right. So, f from x to c continuous and f vanishes at infinity, right. You can think of real line for example and look at continuous functions vanishing at infinity. This is actually a Banach star algebra, it is actually a C star algebra without identity. Okay. So, this is A is a C star algebra without identity. Okay. So, what is the norm? Norm is the usual supremum norm, right. I have a continuous function vanishing at infinity, right. So, it dies down at infinity. So, its supremum norm is finite, and with respect to the supremum norm, C naught x is a is a Banach space, right, and it has a product just like C of x where x is compact T2, you have the product and you get a Banach algebra, and there is the star operation which is f going to f bar, and that gives me a C star identity there. So, it is a C star algebra, except that it has no identity. Now, how do we bring in identity? You just add constant functions. Okay. So, I will be brief here because we will look at it in more detail later. So, the C0 x tilde, that is attaching the identity, can be identified with the algebra of functions obtained by adding constant functions to C0 of x, right. So, your space would be, you look at a function in C0 of x and you add a constant to it, alpha is a constant function, right. F is a function which vanishes at infinity, and that is why it does not have the identity, right, because x is non-compact and it is vanishing at infinity, then constant function 1 is not there, right, because it does not vanish at infinity. What we are doing is we are simply adding the span of that constant function, that is simply multiplication by alpha, which will give me all constant functions, right. So, f plus alpha. Now, you have the identity because the constant functions are there, and so it becomes a Banach algebra with identity if you use the norm, right. So, norm of whatever we have defined, norm of f plus alpha is norm of f plus mod alpha, right. So, it can be identified. So, C0 x tilde can be identified. So, I will say just identified because there is no norm comparison with C of x tilde, where x tilde is the one point compactification of x. Okay. So, x is a locally compact Hausdorff space. So, I can add one point at infinity and then make it compact, that is my x tilde. Okay. And any function in C0 x tilde becomes a function on x tilde, which is the one point compactification. But the problem is the Banach algebra norm. Okay. So, this norm is not equal to the supremum norm on x tilde or C x tilde. Okay. So, if I have a compact Hausdorff space, the continuous functions on that space comes with a natural norm, which is the supremum norm, right. But if I have an locally compact non-compact space and I look at C0 of x with supremum norm, I add the identity just to make it into a unital algebra. The norm we have used will not give the natural norm on C of x tilde, where x tilde is the one point compactification. Okay. It becomes a Banach algebra, but remember that C of x tilde, where x tilde is compact T2, is a C star algebra. So, it has a better structure, right. So, we will see how to add identity to a non-unital C star algebra and make it into a C star algebra. Okay. So, that is what we will do in the next class. Okay. So, we will stop here.